Module 7, Investigation 7, Period, Amplitude, and Shifts of Periodic Functions. Consider the graph of the function f below. What is the approximate value of the period of f? So we need to find out when it starts to repeat. The first thing I noticed are that it might be easy to measure the distance from tip to tip. This one starts at 1 and goes to about 5.2 for a total distance of 5.2 minus 1 or 4.2. So to me it looks like it's about 4.2. 4.2, I don't know if those are radians or what. Let's see, how else could we look at it? Like this looks like a good starting point. Like we could see what happens as we go from this point here to this point here when it starts to repeat again. And that again looks like from 0 to about 4.2. So let me check the answer key. The answer key says 4 pi over 3. And if I jump onto my calculator and type 4 pi over 3, it's 4.11879, which is pretty close to 4.2. So how did they get 4 pi over 3? Well, I'm guessing it's hard to say how they got that. There's no explanation at all in the answer key, but it looks like, let's say we start here, there's a 1 revolution, 2 revolutions. Yeah, I don't know how they got 4.3. That's weird. 4 pi over 3. So yeah, it's 4.2. If you know how to get 4 pi over 3, let me know. That would be interesting. What is the approximate value of the amplitude of f? So notice that this function sort of revolves around this horizontal line. Then the amplitude is this vertical distance from that horizontal line that goes through the center of the function. So the length of this vertical distance is the amplitude, and that's 1, 2, 3, 4, 5 units. So the amplitude appears to be 5. And that is indeed what the book has for that one. To find a formula for the function f, let's see. So it looks like it's a sine function. It starts here and then it goes up and down. Notice that there's a vertical shift though. It's not at the origin, it's shifted down 2 units. So we could say f of theta equals -2 plus our amplitude of 5 times sine of theta. But we can't use just theta because we have to have our coefficient has to do with the period. The period is 2 pi over b, and that b is the number we want, 2 pi over the period, or 2 pi over 4.2. If you do use your calculator, you can just get the number and put it in there. If we used the exact 2 pi over 4 pi over 3, let's see what we'd get. Pi's would cancel out. We'd have 6 over 4, or 3 halves. We should get about 1.5 if we plug that into our calculator. Okay, so here's our function. -2, that's the vertical shift. 5 is the amplitude, sine of 1.5 theta. And that 1.5 is not the period, but it has to do with it. It's actually the 2 pi divided by the period. A bike is on the rack at a bike shop so that the tech can turn the pedal with his hands, causing the bike's back wheel to rotate as well. On this bike, the circular path swept out by the pedal is exactly the same size as the circular path swept out by the tire. Suppose that when the pedal starts at the 3 o'clock position, the tire valve on the wheel is pi over 4 radians clockwise from 3 o'clock in quadrant 4. That's interesting. So here's the tire. Here's the 3 o'clock position. We've actually shifted clockwise to, that's pi over 4. So just a quarter of the way to negative pi over 2. We call that negative pi over 4 is the angle there. Assume that on this bike, every 1 radian rotation of the pedal counterclockwise, the back wheel concurrently rotates 1 radian counterclockwise. So if we have our circle for the pedal right here, if it rotates 1 radian, then this tire rotates 1 radian at all. And here's our tire valve. So let theta equal the angle measure of the pedal counterclockwise from the 3 o'clock position in radians, so the angle that the pedal revolves through, and fill in the following table to show the angle measure of the tire valve from the 3 o'clock position in radians corresponding to various values of theta. So notice that we've started behind. If the pedal's at theta is equal to 0, the tire's at negative pi over 4. And so we're always just pi over 6 behind. This one would be pi over 6 minus pi over 4. Which, if we go ahead and just do that off to the side, really all you have to do is 1/6 minus a fourth. Put that in your calculator, then put pi with it. I'm going to keep the pi's while I show you this derivation. We need common denominators. Multiply this one by 4 over 4, we get 4 pi over 24. Actually, 12 will actually work better as a common denominator. We'll multiply the top and bottom by 2 to get 2 pi over 12. Here, multiply the top and bottom by 3 to get 3 pi over 12. And then 2 pi over 12 minus 3 pi over 12, that's negative pi over 12. So that's our angle here. And likewise, just subtract pi over 4 from each of these, and we get pi over 2 minus pi over 4 is pi over 4. This one let's just keep as 2 minus pi over 4. 4 pi over 3 minus pi over 4 comes out to 13 pi over 12. This one let's just keep it as 5.5 minus pi over 4. You could get decimals if you really want. And 2 pi minus pi over 4 is 7 pi over 4. What is the angle measure of the tire valve from the 3 o'clock position when the pedal angle measure is theta radians from 3 o'clock? The angle measure of the tire valve equals theta minus pi over 4. It said to write an expression. I actually wrote a formula. This is all you need. This is an expression. As the pedal and wheel turn together, is the tire valve ahead or behind the pedal? I think it's behind, because we're always pi over 4 units behind. Define a function p that outputs the vertical distance above the horizontal diameter of the pedal in terms of the angle measure theta. So p of theta, that's just going to equal sine of theta. Since we want our output in radians, we're just talking about the pedal. Just circular motion, you can get that vertical distance above the horizontal diameter with the sine function. Find a function t that outputs the vertical distance above the horizontal diameter of the tire valve in radii in terms of the angle measure theta. So we know that, let's see, we'll actually have the angle measure of the tire valve is theta minus pi over 4, so we're going to have some form of sine of theta minus pi over 4. I think that'll be it. Yeah, since we want, again in radii, we don't have to worry about a leading coefficient here. Fill in the missing table entries with exact values for the output values of p and t. Well, p of theta is the pure sine function. Now, I don't know how you guys are supposed to know the exact values unless you use the unit circle. This could be a good time to introduce the unit circle and make you guys memorize it. We probably have to do that sometime soon. Probably sine of 0 is 0. Sine of pi over 4 is the square root of 2 divided by 2. Sine of pi over 2 is 1. Sine of 3 pi over 4 is the square root of 2 divided by 2. Sine of pi is 0. Sine of 5 pi over 4 is negative square root of 2 divided by 2. Sine of 3 pi over 2 is negative 1. Sine of 7 pi over 4 is negative square root of 2 divided by 2. Sine of 2 pi is 0. And that is blank. Okay. So sine of theta minus pi over 4, so pi over 4 minus pi over 4, that sine of 0 is 0. This is kind of cool. Everything's just going to shift down one space. Sketch and label the graphs of the functions p and t on the axes below. Sketch only the cycle of each function that corresponds to the values in the table. Alright, so I have all these pi over 4 values. Okay. Sine starts at 0. If I say this is pi over 4, then we go up to square root of 2 over 2, which is 0.78. So let me just call this 1. So we go up to about right here. Then at pi over 2, we're at 1. Then we come back here. We go to 0. Then we go to negative 0.78, negative 1, etc. Okay, so something like that. And then if I want to graph the next function, t of theta, everything's just shifted. So when the input is pi over 4, I'm at 0. So I've actually shifted to the right. All of these points just get shifted to the right, pi over 4 units. There we go. Two graphs. This minus pi over 4 here signifies that we have a horizontal shift to the right pi over 4 units, a horizontal translation. Yeah, so notice it's kind of opposite of what you might think would happen. You might think the negative would shift it left, but it actually shifted the graph to the right pi over 4 units. Put your finger at 0, 0 on your graph and run it slowly along the input axis to represent. Does the cycle of t increasing theta values. Does the cycle of t begin and transpire before or after the cycle of p? Does this agree with your answer to part C? So this question, it's kind of strange. You could think about the cycle beginning anywhere you wanted, but if you're talking about the cycle beginning from the 3 o'clock position, if we put our finger here and run it along the input axis, we don't get to the 3 o'clock position like with t until after p already starts cycling. And really this graph could be extended down to down here. But I'm just going to type the answer from the book. The graph of t represents a shift to the right of the graph of p by pi over 4. Why does it make sense for t to be thought of as shifted to the right? How does the function rule for t represent a right shift of the graph? Well, the function rule represents it by subtracting the pi over 4. That's how we know there's a right shift. And it makes sense because we're lagging behind. We start at later input values. So the input value or the output values where the two are equal, they're going to be later values for or greater values for t than p. The book says the tire valve lagging behind the pedal by pi over 4 radians means the tire valve cycle of output values will occur over an interval of theta that starts pi over 4 radians, quote, later. For increasing theta on a horizontal axis, later means to the right, greater values of theta. Thus, shifting a set of output values to the right represents setting them back in the context of an increasing input quantity. The function rule t of theta equals sine of theta minus pi over 4 shows that the argument into sine is an angle that lags behind theta by pi over 4. Thus, the output values will be plotted later in the context of increasing theta, that is, to the right. So, I would just say, hey, the function rule represents this by subtracting pi over 4 from theta. A lag means that we have greater values of input corresponding to equal values in output for the two functions. Something like that. For the same bicycle context as in number 2, suppose that when the pedal is in the 3 o'clock position, the tire valve on the wheel is pi over 6 radians counterclockwise from 3 o'clock in quadrant 2. Okay, let me draw this. So here are maybe like my pedal trajectory, and then for the tire, we start pi over 6 radians counterclockwise. So we start a little bit ahead, pi over 6 radians ahead. The tire still rotates 1 radian counterclockwise for every 1 radian the pedal rotates. And theta equals the angle measure of the pedal counterclockwise from the 3 o'clock position in radians. Consider the function f of theta equals cosine of theta. Explain the meaning of this function in the bicycle context. So given an input in radians, that's theta, the output of f tells us the horizontal distance the pedal is from the center of the circular path of pedal rotation in radius lengths. So if we want to sketch this using domain from 0 to pi over 2, let's see, so here's my theta here. This vertical axis is going to be horizontal distance. And I want a pretty big graph. Let's try to make this go pretty big. I'm going to go over 4 units and have pi over 2 be right here. 4 more. Here's pi. 4 more. We'll get to 3 pi over 2. Then 4 more to 2 pi. call this 1. Here's -1. When theta is 0, that means we're at the 3 o'clock position right here, and the horizontal distance from the center is 1 radius. When we go to pi over 2, the horizontal distance from the center is 0. We go to pi, the horizontal distance is -1. It's really the horizontal position. Then we go to 3 pi over 2, or 0 again, and then we go to 2 pi, we're back to 1. So we have a graph that goes sort of like this. Nope, that's pretty bad. 1 point, this point is too high. Something like that. Now this is 1 full period, because then we just start repeating the same sort of pattern. But if that's the domain, then that's it. As the pedal and wheel rotate together, where is the tire valve on its circle of rotation compared to where the pedal is on its circle of rotation? Well, it's ahead by pi over 6. Let's see, it's ahead because it starts at an angle pi over 6 radians more than the pedal. Write an expression that gives the counterclockwise angle of the tire valve from the 3 o'clock position in terms of theta. So it's always theta plus an additional pi over 6. So if the tire valve is ahead of the pedal by pi over 6 radians, its angle measure is always pi over 6 radians greater than theta. Write a function g that outputs the tire valve's horizontal distance from the vertical diameter in radius lengths as a function of. Write a function g that outputs the tire valve's horizontal distance from the vertical diameter in radius lengths as a function of theta. So we want horizontal distance, that would be cosine of theta plus pi over 6. On your graph in part B, the cycle of F for the pedal begins at theta equals 0. Given that the tire valve is pi over 6 ahead of the pedal, will the corresponding cycle of G start before or after the cycle of F on the graph? I think that it will start before. It says, hint, put your finger at negative pi over 2, 0 on your graph and run it slowly on the input axis to represent increasing theta values. If the tire value is pi over 6 ahead, where will it begin its cycle relative to the pedal? It will begin before pi over 6 to the left of where the pedal started on the graph. And so on your graph in part B, sketch this cycle of G representing the tire valve making 1 full cycle from 3 o'clock position to the 3 o'clock position. So we just have to take our graph and we're gonna just be starting pi over 6 to the left. So maybe like about right here. And so we're just a little bit behind. How does this work? We're going to be at the we're going to reach that bottom value before, so like right here, and then we're going to go up Yeah, something like that. Is the graph of G the same as the graph of F, shifted left or right? Yes, it is the same as the graph of F, but shifted left. But shifted left pi over 6 units. And we have a plus here, and that plus signifies we have a horizontal shift left pi over 6 units. A bike is on the rack at a bike shop so that if the tech turns the pedal counterclockwise, the bike's back wheel turns counterclockwise also. The tire valve on the back wheel is 12.5 inches from the center of the wheel's rotation, meaning that's our radius. Let theta equal the angle measure of the pedal counterclockwise from the 3 o'clock position in radians for each of the following pairs of functions. The second function is a transformation of the first. The second function of each pair has an output quantity related to the tire valve on the back wheel of the bicycle. State the meaning of each function and describe how each pair of functions and their graphs are related. First one, A, is f of theta equals sine theta, and g of theta equals 12.5 sine theta. Okay, so theta is the angle measure of the pedal counterclockwise. So the function f as its output gives the vertical distance of the pedal or the tire valve in terms of radii. And g gives the vertical distance of the tire valve in inches, because we're multiplying by the radius there. And sine of theta, it's in terms of radii, really it's just like the percentage of the radius. So anyways, also let's see how their graphs are related. The graph of G will be stretched by a factor of 12.5. Its amplitude will be 12.5, whereas the amplitude of F is 1. So make sure that that makes sense. You should be able to think about that in terms of a graph. Let's see, so here each of these functions, let's see, so H represents horizontal distance of tire valve from the center in inches, and J, let's see, represents a tire that is pi over 3 radians behind that described in H. The graph of J is, let's see, shifted to the right, or the graph of J is the graph of H, shifted pi over 3 units to the right. It's a horizontal shift, right, pi over 3 units. Okay, let's see. In this one, each of these horizontal distance of tire valve, or sorry, vertical distance now that it's sine, from the center of motion, but Q, let's see, has a different period than P. The period of q is 2 pi over 2, or just pi. So it rotates quicker. Cosine of theta and cosine of theta over 3. So now that we're just back to a plain old cosine of theta function, r could, like the output of r could be the horizontal distance from center of rotation in radii for either the pedal or the tire. And then s is also a horizontal distance in radii, but the period is different. The period of s is 2 pi divided by 1/3, which is 6 pi. And then lastly, let's see, v is vertical. Really both v and w represent vertical distances above the horizontal diameters of the circle's circular rotation. But w is shifted pi over 2 units left on the graph. Cool.